Greetings, ladies and gentlemen. Welcome to this evening's presentation. I just wanted to open up with a few words of acknowledgement, in particular, and homage to the beautiful Moana. This instrument here, noted as the Pūtātara conch shell, also known as the Pūmoana, utilised to alert traditional communities in former times of the arrival of guests, of the arrival of sometimes enemies, but we know we will come yesterday, and also the arrival of new kids, our children in the village. He's opening up with the Pūtātara this evening to commence our presentation, and I was given 5 minutes, but I think I can do it in 3. For those of you who don't know me, my name is Harmonies, turning to Bulata. That's not a tongue twister. You can call me Taha. Some of the students here call me Big T. I'm not too sure why. But it seems to have stuck. We welcome you to the University of Waikato, University of Waikato, Moana. Welcome you once, twice, thrice. I just want to conclude with a brief synopsis of this instrument here. Traditionally an aerophone type instrument, wind instrument, as I stipulated earlier, utilised to bring attention to the multitudes. 1642, there was a record of the Dutch explorer David Tasman arriving at the top of the South Island, Golden Bay. In his diaries he recalls hearing what could be described as the Pūmoana, with the Pūtātara, upon his arrival in the bay. Of course, he was probably the least arriving that people were simply the arrival of David Tasman. The goddess attached to this form deity is Moana, the guardian of the ocean. Some say some tribal variations that she had a bit of animosity with our primordial earth mother, that's Rānuku. She's also considered to be the embodiment of land erosion of the ocean, taking away the land. She also has many children, and the shell, the conch shell is one of them. So the official law in Moana is the atua attached to the Moana. So with that, folks, I will wrap my few minutes up here and just extend my acknowledgements to Dr. Simon and our special guests here. We're in for a treat, folks. So I hope you stocked up on the coffee and tea. And like I said earlier, tēnā utu, apati, kia ora tātou katoa. E mai iwi, kia tōpatahi, kia potahiha, tātou tātou e na tātou, ka hiru koto pā, kia ora e, kia ora tātou.
Hello everyone, can you hear me? No? So good evening everyone, welcome, no mai haere mai, tēnā koutou katoa. So nice to see you and thank you so much for coming out is it still wet out there? A little bit. Would you like just to introduce yourself to your nearest neighbour, please, and say hello? I'd like to introduce our very distinguished guests. And so thank you, Taha. And we've got Marion Arts on guitar, we've got Rachel Jenkins on piano, and Hugo Broad on the French horn. So welcome, you guys. Thank you so much for coming. Yeah. So the pututara, the trumpet, and it's the, I suppose it's a musical instrument that is ready to make a signal. So usually in wartime, and of course the voice carries much stronger of the trumpet than a human voice. So very, very strong, yes? A little louder. So I might just have to go over here. Can you hear me now? Is that better? Is that better? That should be better. And the ko'o is an instrument which is like a flute. So it's I suppose it would be an aerophone and has 3 holes, and it's using a pocket of air that vibrates. So I'd like to talk about not all musical instruments, but some of them. I'd like to go through some waves and sound production and the phenomena of resonance and animal communication, and of course some celestial delights. So we'll see. This is an ambitious lecture, but we'll really try and cover a lot of these subjects, which I think are really important in terms of integration between two really important disciplines, that's music and physics. And I'll start with this quote. We all know that Einstein was extraordinary, as a physicist, but when I read this quote many years ago, really got me thinking. This is a man who, not a theoretical physicist really, not experimental. So it's not like Ernest Rutherford. Many of his formula he dreamt, he imagined, he created in his mind. And to say sort of this is quite profound, to actually think in terms of music, his daily life. And one thing that Einstein did too was he always travelled with his violin. He always played every day. So let's get to instruments. So there are 4 different types of instruments, and the first one are the chordophones, which are the guitars, ukuleles, harps, pianos, anything with a string. And the string is always attached to 2 nodes. So nodes are where there's no vibration. So on a guitar, you've got the bridge and you've got the nut on the fingerboard. And between those nodes, between those 2 stationary points, the string vibrates and causes a frequency. And the body of the guitar is what projects the sound. If there was no body of the guitar, no box around the guitar, you wouldn't hear anything. You would just hear this thud of the string. So it's the air hole and the body of the guitar that projects the sound. With aerophones, that is trumpets, flutes, oboes, harmonicas, bagpipes, didgeridoos, they all involve a pocket of air. So air has mass, even in this room, there's a lot of air. And the air has weight, like one cube, if you think of 1 meter by 1 meter by 1 meter, 1 cube of air, do you know how much it weighs? 1 kilogram. Isn't that amazing? Like, if you could squash that air down and weigh it, it would weigh 1 kilogram. So, air has a lot of weight. And it's that weight, that mass, that medium, that's how sound moves. So you have to have a medium for sound to move in it. And that's the reason why a trumpet will work, because you have a pocket of air inside that, various pockets of air because of the valves. And that's how the instrument works. Idiophones are a little bit different. Because it's instead of a string and a pocket of air, you've basically got a piece of metal or a piece of wood that's donged, okay, or hit, and it's struck. So the vibrating metal or the wood is the one that causes the vibration, and of course what's around it vibrates. So that's what causes the waves. And then of course you've got membranophones. So these are just drums. So it's really like a stringed instrument, except the string is stretched and like a skin and a membrane, and in the middle is your antinode, and in the outside is your node. So the node is where no vibration occurs. Okay, a little bit like the nut and the bridge on the guitar, and this is where the main movement of the drum is, in the middle, in the center. And of course, bigger drums, large drums make low notes, and small drums make higher notes because of the diaphragm, the diameter of the bigger the drum, the lower the note. Okay, a little bit like on the stereo system, you've got your woofer, which is the big speaker that will produce the low pitch, the low frequency, and the tweeter is the smaller speaker that generates the higher frequency. Castanets are old, very, very old instrument, and dating back to 1000 BC. So from the Phoenicians. So this is North Africa, and of course they swept into Spain and had a huge influence with flamenco music. And the castanets are, well, they're like a wooden shell, really, and they're made of chestnut wood or ebony, something hard, very hard wood, and you can see that they're hollowed out like a concave. So when they're hit or clicked, they again project that sound through the hardness of the wood. So really beautiful, very, very simple instrument. But it's not the oldest instrument. Do you know the oldest instrument ever? Who could tell me not the hand? No. Well, you could have, yes, the clap, the human voice, yes, it would be but this is it. Well, this is what I think. It's the Neanderthal flute. It's 42,000 years old. And of course, in that time, the Neanderthal and modern man were together. They roamed the planet, obviously doing a little bit of mixing. So anyway, yeah. But I was fascinated with the holes, because I was thinking, how do you get holes in a bone? They must have had a very sharp piece of like obsidian and really drilled down, because I suppose the bone would be soft. But lovely symmetrical holes there. So yes, the good old Neanderthal played music. I go to the Renaissance lute because it's a very, very early instrument. Probably, 900, 1000 AD, probably. And why I've chosen this, because really the precursor to a modern guitar. And it's got an interesting course of 20 strings, and they're paired. Okay, so they're paired strings, and they're made of, like sheep's gut or goat's gut. So not nylon or not wire. And each pair is an octave higher than the other. They're not all the same. So each note is paired with an octave higher, and it gives it a much more brighter sound. Because as you can see, it's a bit of a flat instrument. The air hole isn't very big. It's lovely and ornate and well made, but I would say that projection, it wouldn't project very well. So having double strings makes the sound brighter. This is another shot. It's got a curved back on it. So definitely having the curved bowl-like body of the lute would project the sound into the room. And then we've got the sauterne. Now the sauterne was very popular in the Renaissance times, and we're talking about 1300, 1400. It's a lot smaller and very portable. So, off you'd go with your little sauterne in the evening, and you could go and meet friends, have a few drinks, and play. And this is an interesting instrument in that it had steel, wire strings. So there was a big change. Instead of gut, they went to steel, steel strings and no double strings. So 10 strings. You can see the headstock on that. Then we move into the vihuela, and again, you're seeing the construction of the guitar with 5 sound holes. Again, trying to project the sound out from the body of the guitar. And, made of cedar. Cedar is a nice light wood with a lovely warm sound. And you can see the Stradivarius, the sort of classic shape of the guitar being evolved there with the one air hole. And this is the bracing of the guitar. And you can see the changes there between the fan bracing. This is on the top plate of the guitar. So again, to give it construction, keeping it strong, but at the same time, again, projecting the sound. This is Antonia Torres. It's probably the first classical guitar. So made of cedar, 6 strings now. See the evolution? No longer paired strings, no longer 12 strings. Get down to the basics of 6 strings and nylon strings. Okay, so look, and pegs in the head there. Ebony fingerboard, probably with rosewood in the neck. And this is the modern day flamenco guitar. No longer a cedar, probably a body made of, cypress or sycamore. Now, cypress is similar to the cedar, but it has a brighter sound. And that's what you want for flamenco, because usually flamenco is played in courtyards out in the open. So you want the sound to be projected well. It's in the Renaissance time, most of the music was played inside. But with the flamenco, it can be played indoors, but a lot of the flamenco dancing and stuff is outside. And this is the reason why the guitar had evolved and the brighter sound. So 6 strings on the guitar, and these are the frequencies here. 65, all 65 centimeters long, but they all produce different notes. And the reason being is because they've got different weights. A heavier string, which is your low E, of course will vibrate at a lower frequency than the thinner nylon string. And that's the reason why they have different notes, because they're all at the same length. And I'd like to invite Marion. Can you give her a hand, please? Thank you, Marion. It was wonderful. Can you give Marion another hand, please? Do you want to know anything about physics now? Here we go. You did come to hear about physics and music. So anyway, no, but the parts of a wave are really important to understand. So I think everyone understands there's a crest at the top of the wave and a trough is at the bottom of the wave. But one of the most important things is the wavelength of the wave. So if you take any point on the wave, it doesn't have to be a crest, then the next consecutive point, so if I took it from there, that's the wavelength. So the wavelength of a wave is really crucial to understand because that influences a lot of things like the frequency and the traveling and the velocity of the wave. These are traveling waves. So they're going from a source to somewhere, okay? They're traveling. So higher notes have there are more cycles per second. So there's a greater frequency, okay? Smaller objects are generally vibrate faster because they're denser. They're usually smaller and therefore the vibrations are quicker through the medium. When you've got a large object, the vibrations are longer. They take longer to get through, okay? And this is an interesting point here. Any two notes that are an octave apart have a very similar sound quality because the higher note vibrates exactly twice as fast as the lower one. And then we all know that the notes, in Western music, the notes are from A to G. This is important too, the wave equation and how you build your understanding up from that. And I think most people understand that speed is distance divided by time, and it's like kilometers per hour. So the wave travels through a distance divided by its time. But we know that the frequency is always inversely proportional to the period. So that means, if you've got, like the period is the time of one cycle. So the moon goes around the earth, it takes 1 month. Okay, so that's a period, that's one cycle. The earth orbits every 24 hours. So that is one cycle. So that's the period, that's the time it takes. Now the frequency is the inverse of that. So it's the number of cycles per second, okay? So that's a very important formula or relationship to understand between frequency and the period. Now if we put the period down there, big T, okay, and that's the wavelength, so it's the wavelength divided by the time, we can come to this formula here because we know that the frequency is equal to 1 over the period. So here we've got the wave equation. So velocity is equal to the frequency times the wavelength. Now, why I spend so much time on this, you might be bored already and you can leave, but usually the speed in a medium is the same. So the speed of water is within that medium, it remains constant. It's the same as the speed of light. It remains constant in the universe. Okay, so if you take the speed of light in space, it's always 3 times 10 to the power of 8 meters per second. So the only two things that can change and affect one another are frequency and wavelength. Okay, and these are really important to be able to calculate in the universe. Now, you might think sound just comes from instruments, and of course, back on the planet, of course, we know that animals make sound, and I chose the sperm whale because it's just an extraordinary animal. I mean, and we've got quite a few of them on the east coast of the South Island. They dive to 3 and 4 kilometers deep. So, 3,000 meters down, and basically they are swimming in darkness. They can't see it. There's no light whatsoever. Once you get past, 1,500 meters, there's very, very little light down there. So their adaptation, of course, is to use echolocation. So they're basically making a sound, usually clicks, and they can detect that sound. So they emit the sound, and then when they receive it, the brain can work out where the prey is, how fast they're going. So they use echolocation, or like sonar, to find out their habitat, where they're at, where they're swimming, and of course their prey. Every sperm whale has its special coda, has a special dialect, a language that it uses with other whales. Two mating whales usually use slower clicks. Okay, so there's a different range of clicks used within the pod. So I will just show you. Oh, this is the echolocation. So basically, that only happens in toothed whales, dolphins, and sperm whales, but also bats. Bats use echolocation, another mammal. So emitting the signal and returning the signal. Isn't that an extraordinary video? You know, every time I watch it, I'm thinking, wow. And I love the way the whales are together with the calf. You know, they're really protective of the calf, and the calf's only a few days old. Did you see? There's a little bit of the umbilical cord still left on the whale. So yeah, incredible and amazing that they turn upside down. They swim underneath the calf just to protect the calf. So yeah, quite an extraordinary animal, and this is of course how it works. They have these kind of lips, phonic lips. The air gets sucked in at the blowhole, and this is where the sound is generated, is made, and whizzes back here to the air sac, and then it's beamed out here. So the sound is thrown out and emitted through the head there of the whale, and this is the air. So it's received through here. So it juts out there and returns underneath the underneath the whale there. And I always worry, I'm not sure, about this sand mining, on the west coast of in Taranaki, how this will affect the whales, because we've got blue whales coming up on the east coast of New Zealand. And, how will they cope with all that? No one talks about the noise of the sand mining. Everyone talks about, the dust and the debris that it creates. But I always think, well, what about the sound? The sound will, of course, be much more amplified in the water. So, but I haven't heard anything about that. So is there sound on Mars? No, there's not, no. So, and I remember watching this movie, The Martian, with Matt Damon in it, and I was looking at the suit, and I'm thinking, I don't think that's going to do it, because it's too thin, I mean, it's so cold on Mars. Mars is the next planet away from the sun, and, the average temperature is about sort of negative 50 degrees Celsius, So, and it looks hot, doesn't it? You think, you're in a desert, and be sweating. But no, it's just so cold. I mean, in midday, there are parts of Mars that does get up to 20 degrees Celsius. But of course, there's no air. It's like 1% of what the atmosphere is on Earth. So, I mean, if you took that helmet off for just 30 seconds, you'd die. You lose pressure immediately. And of course, we live in a pressurized system. We live, at 101 kilopascals in this room. That's how we can breathe oxygen. So, yeah, on Mars, no. And of course, no sound, because there's no air. So it doesn't matter how much you scream, even if you did take the helmet off, it doesn't matter how much you screamed out, the sound wouldn't travel. So yeah, we need air. So sound waves are longitudinal waves, so that means they're basically pulses. It's like a pulse. You're hearing my voice through a pulse through the air. The sound is leaving my voice and it's going to your ear through air, through the particles of air. Okay? If we took the air out of this room, you wouldn't hear me, So, speed of sound in air is 330 and the speed of sound in water is 1,000. So it's much, much faster in water, Pitch is important. So low frequency, if you've got a low frequency, you have a long wavelength. So frequency drops, the wavelength increases, okay? If frequency goes up, so your pitch goes up, frequency goes up, then of course the wavelength shortens. So very, very high frequencies, the wavelength shortens down. So it's like the opposite, okay? And this is a very important slide. I know it doesn't look very exciting, but these are nodes. So this is where no vibration occurs. And this is what happens in all musical instruments, whether you've got strings or whether you've got columns of air. This is what happens. You've basically got a standing wave. So the wave is generated inside the object, but it reflects back on itself and it's trapped. So a standing wave is a trapped wave. It's a trapped traveling wave and can't get out. And so it produces these nodes and antinodes, okay? So yeah, it's very important that you understand that. And then of course the next thing is these are the harmonics. So harmonics are the fundamental frequencies that you find in, open pipes, closed pipes, and strings. And there you can see there's the first harmonic. So so when you twang the string of a guitar, it goes basically up and down, and that's what the first harmonic is. Now at the same time, it will also make the second harmonic, which is a half of that. So at the same time as it's going up and down like that from the two nodes, you will get another second harmonic. So there are a number of harmonics every time a string is plucked. Okay, it's not just the first harmonic. There's a spectrum of sound that comes from that string. So it's like a kind of a rich fruit salad of frequencies that comes from that plucking of the string. And it's the same thing with a closed pipe and an open pipe. Closed pipe is what you would call, like a whistle. A whistle would be a closed pipe. And open pipes like didgeridoos, flutes, those sorts of things. And this is where you're getting timbre or tones. So they're all playing the same note, but why do they sound different? Well, they sound different because, they sound different because they're different instruments. They've got different bodies. They have different timbre, different shape, and they all are producing the same fundamental note there. You can see that it's peaking, but because they're producing all these mix of harmonics in each of the instruments, and that's why they sound differently. Even though they're playing the same note, they sound differently because they've got a spectrum of different frequencies. This is probably a better example because the tuning fork always plays the purest note. So there it is there, there's the frequency there, and you can see the saxophone is playing that same note, but look at all these other harmonics that are coming in from that instrument. So the spectrum of sound is so different from each of the instruments, even though they're playing the same note. This is a nice picture. This shows a lot because here you've got the note of G4 here on the flute, and look at the dominant frequencies here. What does that say? 392, 784, and 1176. So those are the dominant peaks, and that's what you hear. You will hear those frequencies, but look at all these others. And so that's why each instrument has its own signature or unique range of frequencies that it emits. I just want to go to the harpsichord because I know Bronya loves the harpsichord. Where are you, Bronya? And this is a really interesting instrument because the strings are plucked mechanically. So it's like a piano, but the piano, has a hammer on the string, whereas the harpsichord, and in very, very, quite posh households in the sort of Baroque and Renaissance time, that's what you would have. You'd have the harpsichord rather than a TV, and people would be welcomed and you'd play. Wouldn't that be lovely, in the evenings? So, but lovely instrument here. And this is the musical scale, so music intervals. So here you've got A and 1 octave, and so the next A will be double that frequency. So you've got 220 hertz when the A is played, and the next A is 440 hertz. So we call that 1 octave. So basically double the frequency. Rachel. Can you give another hand to Rachel, please? So when you drop a spoon and a tennis ball onto the floor, they sound different. It might sound a bit it sounds a bit stupid that, but they because they hit the floor and they vibrate differently because they're different objects. And what the collision creates this vibration, and that's what we hear. And every object has its signature natural frequency. If the vibration is forced in any way, so if you drive the force of the vibration at its natural frequency, it amplifies the sound, and it can cause havoc. And you'll see in this next slide, really, this is the Tacoma Bridge, and the Tacoma Bridge fell apart because the wind wasn't that strong that day. It was just at that flow through the bridge, and it caused a standing wave. And you'll actually see the nodes and the antinodes in this bridge. So this is what happens, is that when you have a harmonic or a standing wave, it's a bit like an opera singer can just get the right pitch and they can break a glass. So the forced vibration matches the natural frequency.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
This is another little quick video just to show you this is what they do when they test buildings for earthquakes. Because again, an earthquake is a forced vibration underneath the building. And this is done in the laboratory, and basically it's a spinning motor on a little platform, and you'll see the standing wave in the structure here. This is an interesting slide because it's just it's a steel plate, and it's got sand on it, and these are the nodes and antinodes. So this is a node where the sand accumulates. is a no because there's no movement. And where the black or the dark is the antinode. And look at the different, basically the plate is being moved, it's vibrating. And look at the different frequencies and the different harmonics that's made. Okay, and of course a steel drum, from Jamaica uses that system. And this is an interesting slide here because at low notes, look at the harmonics there. This is X-rays of the guitars, and as the higher the pitch, this is 1194 hertz. Look at all these harmonics in the guitar. So the harmonics are very real within the body of the guitar. Hugo on the French horn. Can you welcome Hugo? Can you give Hugo another clap, please? And that's all to do with, air in a little chamber. And if you want to make a musical instrument, you can make one in your front garden. This is what I did. And the neighbours love me. All you need is a pair of jandals. And these are just PVC pipes. So they're just cut down at various lengths. So, you've got the D at 150, that's the short length. And you've got another D at 2 meters. And it's amazing. You can make beautiful music out of PVC pipes. I want to take you to, of course, we've got to have some celestial pictures because it's my real love is astrophysics. And I just want to take you to a neutron star because everyone raves on about black holes, black holes, black holes, and of course black holes are extremely interesting, well, some people think, but it's the neutron star that really takes the cake. And because this is how a neutron star is made. So basically, you've got a very big star, really much bigger than the sun, our sun, okay? A big red supergiant later on, after quite a number of million years, and then boom, supernova, an explosion, and this leaves either a black hole, because the gravitational attraction basically drops down and even light can't escape from the entity, but it's the neutron star. And this is a tiny, tiny little star. It's only about 10 kilometers across, and it's got huge amounts of neutrons in it, and it causes an enormous gravitational attraction and a very large magnetic field around it. And the interesting thing about the neutron star is that it spins, and so they're called pulsars, and the pulsar will rotate and spit out not sound but radio waves. And these radio waves, and all sorts of other things like, alpha particles, gamma rays, all sorts of things, and they are called the cosmic lighthouses because you see them up in space. They basically rotate at different frequencies, and they're actually sending out a signal that we can map, we can look at. So it may not be sound, but they have their own music, they have their own frequency that we still don't know enough about them. And so, there's so much exploration going around there. And of course, what they do, they come to the Earth's atmosphere and they create this cosmic dance. And it's this, what we call cosmic entanglement, where you get interactions and it makes this beautiful dance, all these incredible patterns that are at random, but also at, quite a beautiful pathway. And again, we still don't know enough about this. And, I find this really fascinating. So the cosmic dance from neutron stars. And I'll just take you to the last couple of slides. This is Messier 51, the whirlpool. So it's normally it's the most magnificent galaxy, and you find that just below the plough. We don't see it in the southern hemisphere. You've got to go north to see it. Yeah, and there's neutron stars in here, So so this is the last slide for the evening, and I won't dim the lights, but this is probably the most extraordinary photograph ever, because these are galaxies. Every patch of light on this slide is a galaxy, not a star. It's incredible. And the Hubble telescope, which is now not working. I think it is still working, but we've got not the Kepler, the James Webb. Yeah, thanks. We've got the James Webb telescope. But, this is an incredible shot over many, many, days to capture this light. And you know what? We're looking back in time. We're actually looking back in history because many of these galaxies may not be there. So, I'll leave you with that. And these are my final thoughts. Just to blast you away with some cosmic pondering. The more I explore music in the universe, the more I sense that life is a cosmic dance. Our own atoms come from an old star. We are the cosmic dance. And perhaps the universe is a giant guitar that plays the beautiful music. I'd like to thank Marion Can you give Marion a hand, please? And Rachel, just incredible. And Hugo, thank you so much. Thanks very much, everyone. I'd like to thank Nikki too and Parahuia for organising this event. Thanks so much for coming along. It's a real pleasure to talk to you about some physics and music.